now we have the pleasure of having Miguel Ortuno with us. Miguel is a professor in Université de Murcia. He's coming out of retirement time to time in order to give some nice talk and collaborate with people from the field. And we are really pleased to have him with us right now and to fill the gap. Sorry for the change of schedule. And so, Miguel, if you're ready, the floor is yours, and you will present to us a really nice results you have on current bistability in the superconductor insulator transition.
Thank you, Vincent. Okay, first I would like to thank the organizer for inviting me. My field is a bit out of the main core of the talk, but of the conference, but I found many interesting questions, so I hope that with my talk is the other way around for you, so that it's out of your field, but you find interesting questions. I'm aware of that, so I will try to keep out of technical details. Okay, we work in the superconductor to insulator transition, but in the insulating, mainly in the insulating side. So everything I'm going to say today is about the insulating side, where I've been my field for many decades. Specifically, I'm going to concentrate in the stability that hasn't been studied very deeply. I think that it's a very general feature that can have important applications and also give a lot of information about the materials and the process going on in there. So I will present experimental results and one model that explains part of the experiments. As we will see, depending on the materials, results that looks very similar, in fact, they must be very different. That's the main point of it. Okay, first, you all know about this, that we can tune the superconductor to insulator transition by different methods. That's what we're done by changing composition, thickness, heat treatment. Specifically, here we concentrate on heat treatment, where increasing the annealing temperature increases the disorder. So so that we get deeper into the insulating side of what interests us. Here, so we are considering samples, as I said, in the insulating side, but close to the transition. The first thing that you notice is that the linear behavior of the conductivity is activated, and this is not clear why this is so. But for the experiment I'm going to show is important to be activated, because then it's easier to reach. The same should occur if you have variable range hopping, so non-activating behavior. But in this case, by an easy calculation, the temperature where you see this effect is much lower, much more difficult to reach. So to have activated behavior is not crucial, but is fairly important. And the reason of the activated behavior, I think, is not clear at all. Depending on the material, it may be a different source of why there is activation. Okay, here, as I said, a reminder of what possibilities, what type of effect can give rise to activated behavior. I mean, well, just in case, activated means that when you plot the log of the resistance versus 1/3, you get a straight line. When I say activated, I mean a straight line. As opposed to that, in general, in many materials, many insulating materials, you find variable range hopping when you have a curve thing. This curvature, this is saturation. And this is also nice because we can explain now this saturation really well with the model I'm going to talk about. So the different possibilities, one is a mobility edge, meaning there is a band at high energy, and so you have to, in order to conduct, you have to get excited to this band. The other thing is that you have grains or pseudo grains and granular structure, and then you have a charging energy, and then in order to contact again, you jump to a nearby grain, and you have to pay the charging energy. The other thing more related to the talk here is that there is a superconducting gap, so that electron, if you want to contact by electrons, you have to go into grains that are superconducting. I mean, the whole material is not superconducting, but there are superconducting grains, and you have to pay the gap whenever you cross them. The other thing is that this is basically 2D, and then being 2D, you may have logarithmic interactions if the electric constant is large, and logarithmic interactions, according to variable range theory, give you activity behavior. And the last possibility is that you always contact by near stable. Okay, this is the type of experiment. First, I'm going to show two types of experiments. One by the group of Claire with Vincent, and the other by the group of Johnny at UCLA. The first one on yttrium silicon were done by Claire. This sample was annealed at 80 degrees, and so it's relatively is very close to the transition. It's not very insulated. Then you see that changing the voltage, you have here some kind of you see that there are many other magnitudes in the current, so you have some kind of jump, but it's more impressive if you anneal to 95 degrees. So just a bit of annealing produce the sample become more insulating, and then the jumps are by more than 4 orders of magnitudes. So I think that this is a very interesting, very nice effect. That's to try to explain that is the main reason of the talk. No, you have these big jumps, and also you have hysteresis. So according to the temperature, you jump at different temperatures, but then when you come down, all temperatures go down at the same voltage and different, so that so you always have hysteresis here. Okay, there were previous experiments similar to that, but by Obadia and also by Ladier. The ones by Ladier, I think, are very, very interesting, but nobody or few people pay attention to them. And then Boris Altschuler, or authors of them, explain this in terms of the hot electron model. And I'm going to explain what is the hot electron model, because is that basically tells you that you have a strong voltage and some temperature, then the resistance of the system is just the same as it would have at the linear regime, so at 0 voltage, but with an effective temperature. So that as we are in the activated behavior, it means that you always have an effective temperature that you put in this formula, and this gives you the resistance. An important thing is that the fact of having an effective temperature, I think, is a clear indication that the conduction in the insulated regime is not by phonon, but is more by electron-electron interactions, I think, and the role of phonon is just to equilibrate, to thermalize the system. So in a standard theory of hopping in insulator, you assume that the phonons drive the hops, that the hop from one localized state to another is due to phonons. With hot electron, it's not precisely stated like that, but I think that the only way to understand the hot electron model is that the transitions between localized states are driven by electron-electron interactions, and the role of the phonon is just to equilibrate, to thermalize the distribution of the phonons and the distribution of the electrons, the thermal distribution of both of them. Then, okay, too many details. It is fine out experimentally that the power exchange between the electrons and the phonon is given by this expression where beta is an exponent of the order of 5, 6, depending on the dimensionality. This is an expression obtained theoretically for metals, but for some unknown reason, it works very well in insulators also. And there is no reason for that, but it works. So that at the end, the system of equations that we have to solve is this, is that the power, so this is V squared over R, this is the expression for R, so this is the power, the Joule power that you put into the system to the electron bath, and the electron bath exchange power with the phonon bath, so that at the end you have this system equation for the effective temperature. So you have to solve this equation for the effective temperature. This equation cannot solve analytically, but you can solve it numerically. And the curious thing is that there is no one solution. In some regime, there are 3 solutions. So I'm plotting here, these are theoretical curves. So you see that for a given temperature, for a very low temperature, this is the solution of the previous equation. It goes like that, then it jumps here, and it jumps down. The solution, the mathematical solution is this. It comes here, and then it goes like that. It's like an S shape. It goes here, but in reality, once you are here, you don't come back. You always, then you jump to the upper. So you always have 2 branches, 2 solutions. So at a given voltage, you have 2 branches. And okay, then this explains fairly well why you see this is similar to what I showed you before. One thing is that the critical temperature, that is this one where the critical temperature is when you don't have hysteresis anymore, or when you don't have the jumps. So the temperature at which the jumps disappear, this is given like that. These formulas are for activated behavior. There are similar formulas for variable range hopping, but as I said before, the final result is that the T critical is lower, much lower if it is variable range hopping. So this, when you put reasonable values of beta, this factor is like 1/10. So if you have the critical temperature, it is 1/10 of the activation temperature. And this is easily reachable as you saw expect. The other interesting thing is where is the critical voltage? The critical voltage is here, is where you see the big jumps going down in voltage. So the critical voltage is given by this formula. The important thing here is that this is material dependent. This here, this constant is the electron phonon coupling that appears in the power exchange between the electrons and the phonon. So this depends on the material. So in principle, every material should have this transition. The only thing is that if the electrons and the phonons are properly coupled, this alpha is very large, and the voltage, the critical voltage, is huge. So you will never see it in practice. Other effects will occur first. That's one thing that you always should see this transition according to the model, but in practice, it's difficult to see. So why, as I showed before, for the sample close to the transition, you see jumps, but very, very small. For the more insulating sample, you see huge jumps. So it's clear that in reality, sometimes you follow, or sometimes you may follow this model, but in other cases you may not follow. So the rough idea is Altshuler et al. Gave this explanation. This explanation explained very relatively well for some samples, but nobody have done a proper check of the theory on top of the experimental results, theoretical results, and that's what so, okay, before, just a small thing, I talked before about saturation. So this saturation, there are many types of saturation. Of course, it can be saturation by the apparatus, by the resistance of the apparatus, but this is not the case here because the resistance is different. The saturation here can be explained nicely by the hot electron model. Just if there is an external power, if you have external power, then with these equations, then you see that the temperature at the end here, you are not reaching the temperature that you think. So even if the rheostat and the temperature of the funnels is you think that you are at 10 milli-K. Here, for example, for us is around 40 milli-K. The system becomes decoupled, and then what you see is the external power going into the cryostat. So, as I said, in this case, saturation can be explained very well by the hot electron model. Okay, these are the jumps. Here, the color are our model, the results of our model. The black dots are the experimental results that I showed you before. Then you see that the agreement is really excellent. We did that with a global fitting, and the only parameters that we did were the prefactor of the activated regime, the activation temperature, the electron phonon coupling, alpha that I put before, and the external power. And the funny thing is that the global fitting gives basically the same result from the linear regime, where you can obtain R0, D0, and P external. So it's clear that the hot electron model works extremely well. I think that there are few experiments where you can see such an agreement with just 4 parameters, an agreement between so many curves, and precisely with such big jumps. One thing here is that the exponent beta, we took it equal 6. I mean, we tried 6 is the best. We tried a few of them, and we keep it fixed. Well, it's a bit of it may be a tricky thing, but that's what we did. Then, okay, this is the power. So here I plot the power. This is just I times V, and here I put the effective temperature that is obtained in the equation. So you see, these are the experimental curves that that they converge all to a straight line, and the slope of this straight line is 6. So for this reason, we took beta 6. According to theory, beta should be an integer number. So for this reason, as this is very close to 6, we took beta 6 and don't consider this to be a free parameter anymore. All these curves can be merged into this line by plotting here the effective temperature to the power of beta minus the phonon temperature to the power of beta. And here we put the power plus the external power. So putting these things, we get a very, very good straight line over many order of magnitude. And this is the real test of whether the hot electron model is working or not. So if the hot electron model is working, all data could be collapsed, should be possible to be collapsed in this single. Okay, we'll repeat the same thing. This is a bit technical, so I will. Much I have been talking. Okay. So I plot the same the power for the other sum, 85. Then this is the curve for the 95. Then you see that the slope here is much larger. So you say, okay, I change beta. So if you change beta, then you will get a beta close to 8, and one can fit the results relatively well. But I think that this is, from a theoretical point of view, this is really inconsistent, because beta should be an integer and should always be the same, because you are not changing the material. So it would be very strange that beta really changes. The other thing is that the electron phonon coupling is also changing a lot. So there is also no reason for that. So what we think is that in this case, there are other processes of relaxation. So the relaxation before, in the hot electron model, this is our explanation of the hot electron model. What we think is that in the hot electron model, you have grains of pseudo grains that are fairly large, and relaxation is by phonon interacting with electron within a grain. And the reason why the formula of the power works. It's a formula for metal. I said it works is just because the grains are metallic grains, relatively large. So for this reason, this is working. For this case, as this is more extended, then you have relaxation between nearby grains. This is a little bit technical. The thing is that we incorporate this effect and another effect that I will explain later. So, and then with that, okay, this is the explanation of our model. Okay, this is much, much worse than before, but still is not terribly bad. The thing is that, okay, we try 100 mechanisms to get to see this result. So the thing, the message is that if you are right in the insulating side, the hot electron model works very well. But once you get closer to the transition, you have to add new elements, and in practice situation, in many situations, it may be difficult to use that. Okay. Another ingredient that we put to explain this the case for 80, for example, anneal at 80 degrees, is that in the hot electron model before you don't have the term AP. The term AP is very well known in the nonlinear behavior of insulators, and it's called the exponential field effect. But there is with the T. And the problem is that if you include T effective here instead of T, you can explain basically you say most results in nonlinear behavior of insulators. So this is something that we want to work on that. I mean to have a review of how I think that basically all results on now there is like a dichotomy that many people say that some results are explained by that and some by the so what they say if you put here T is the exponential field effect, is you suppress the V and put the T effective is the hot electron model. So now in the literature you can explain with these two models, but we think that putting T effective there, all results can be explained. And the reason for that is that if you jump to a nearby grain, then the charging energy is reduced by the field. So the explanation is fairly easy. One thing, just a small comment, is that the same thing would happen if you have a band. And I'm putting that because I now start to believe that the reason for activated behavior is that you have a band. You really have a band. It's like the upper have a band, so a band of charged state. Then if you have a band of this form, so here instead of coming to a grain, here you are at a higher temperature. The grains overlap more so that they can be extended and form a band. Even if you have a band of this sort, in order to get to this band, you cannot get to the band here because then you are not charged. So even if there is a band, you have to jump to the nearest neighbor, couple to this band, so that this effect should be generated. That's okay. This is just a question. So here I start with the second set of experiment. That's by Johnny at UCL. Okay, so you see this is the same VI logarithmic scale and jumps over 4 orders of magnitude. So you would think that is really the same. But if you go into the details, you see that this cannot be explained at all by the hot electron model, not even including some extra elements as we did before. You know that with the exponential field effect and with extra mechanisms for relaxation, we saw that these big jumps still could be explained by the hot electron model. But here, when you go into the details, as I said, it cannot be explained. And this model has a very nice feature. So I will tell you why it cannot be explained. Here, this is the same as before, but I draw the resistance here instead of the density. Then each of these curves is for a different temperature, and here is voltage. Then you see here extremely well-defined straight lines. And this is a clear indication that the hot electron model is not working. I mean, it's not that it's not working, it's that effective temperature exactly coincides with the phonon temperature. So we are in a situation where the electron phonon coupling is so strong that the effective temperature, by all means, at these voltages is the same as the phonon temperature. So this is the, as I said before, this is the exponential field effect, typical of nonlinear behavior in insulators. And you know, if the hot electron model were working, then what we would see is that the temperature deviates here. Here, maybe, you know, maybe these points indicate that there are small hot electron effects, but they are very small and they are not responsible for the transition, because you see that here, right to the transition, you have a very, very good straight line. So it's clear that there are other indications. I will show you one of them, that the hot electron model is not the driving mechanism for this huge transition. Another nice thing is that if you plot the slope of these straight lines, this is done here, you see that they follow a extremely nice straight line as predicted by the theory. So everything fits very well within this field effect theory. The other reason why it's not a hot electron effect, these jumps, is the following. This is the same as before, but changing this to normal scale instead of logarithmic scale. These are the result by Joyce. And then you see that here you have a extremely nice straight line. These are the results by Claire. The same, so I do the same, but in normal scale. The intensity is now in normal scale. And then you see that here you have some kind, it's not exactly parabolic. This is basically beta to the half. So this is the behavior predicted by the hot electron model. So in the hot electron model, when the voltage is very large, you can see that approximately the effective is just beta to the is b to the beta to the half. So that instead of a straight line, you have this type of parabolic cubic behavior. So these two features is telling us that really the hot electron model is not the reason. Then these are previous work by William and Stemmer, and here you see that you can have this is the different temperature, so that at very low temperature you have things similar to here, that and you have here a straight line. So this experiment was explained by the Wigner-Rista, meaning that you have Wigner physics, and here you break the solid, the Wigner solid, and this becomes a liquid. What I mean, this is preliminary, but what I believe for the moment is that here is not a Wigner, because here these were very clean samples. I mean, there were conditions. It may be a Wigner solid, but here I don't think so. So because here there is a lot of dissolved. So still, I think that the physics is related. It's like here you have here ground state, near the ground state, you have some kind of solid or glass, probably a Coulomb glass, an electron glass. And when you apply enough voltage, then this you have avalanches, and then these avalanches produce a liquid. So the voltage have enough. This is liquid fluid-like, and then you have this linear behavior. This is, I think, is the last slide. This is the linear regime for the last set of experiments. And then you see, again, activated. Oh, one thing I didn't say is that Claire's results are very close to the superconducting side. But Johnny's result, the material is indium antimonide and is not supposed to be superconductivity at all. So in one case, we are close to superconductivity, in the other, we are not. So maybe this is also an indication of why experiment that seems very similar. In fact, they are very different. But the funny thing again is that in this case, even if the material and the mechanisms are very different, you still have activated behavior. So I think that's something that need clarification. Why such different materials you always find activated behavior? Here you have saturation, but this saturation is not the same as before. Before it was external power, then they occur at the same temperature. Here, saturation is roughly proportional to the activation energy. And there are models that explain that, but the models have to be adapted. Basically, this could occur if the energy penalty that give activation is produced by the barriers rather than by the charging energy. So if the grains are big enough and then the charging energy is small compared to the activation energy, then at the barriers the important resistive elements, and then in this case it's predicted that the saturation should be proportional to the activation energy, and this occur experimentally in this experiment, but we don't know if this is the reason. So, okay, okay, conclusions. Okay, this when you see this exponential field effect, from there you can estimate the localization length fairly well. You can also from the activation energy, if you are sure that the activation energy is due to the charging energy, you can obtain the localization length. But there, the dielectric constant enter, and you really don't know what is the dielectric constant. So you can estimate at least the order of magnitude. But in this case, with the exponential field effect, you can obtain the localization length without any other factor, any intervening in that. No. Then I think that these type of experiments are very nice to understand nonlinear effects and give a lot of information, and not so many people have worked on this regime. I don't know why. So the message is, as I said before, is that there are two types of bistabilities, that they look similar, but they are really different. And the last thing is that, okay, the two, I think, main question is why everything is activated. It's necessary to be activated to see these big jumps. And the other thing is if superconductivity plays a role. I mean, in the material, in class result, it's clear that we are very close to superconductivity. But in unit result, theoretically, we are far from superconductivity, but still may be some hidden superconductivity there. We don't know. So this is, I think, an important question. Thank you very much. Questions? Yeah.
For the interesting talk, I have a question about the beginning, the model and the distributive. There's a certain 6th power dependence of the component coupling. So, do I understand it right? You have like a system which forms grains, and then there's like hopping between the grains, but then this component happens mostly inside the grains.
Yeah, that's right.
Because, and then those grains are metallic.
Yeah, that's
but,
right.
But
that's right.
Not superconducting. Because I mean the 6th law you get only in the normal state. If you have a superconductor, there is delta. That also has an activating gap like component coupling. The second point is that usually you get to the 5th power in the 3D metal. 6th power you can get for disordered metals, at least theory by Kaplan. That depends a bit on sort of how the disorder moves. That would require that your grains are also disordered.
Okay, I never thought about this, but yeah, I mean, you may be right. Yeah.
The grains are probably disordered. And to answer your first question, so we see a difference when we go closer to this SAT, this superconductor. So from a purely activated behavior to an activated, an activated, but with a different activated energy, which at least we interpret as beginning of showing some kind of superconducting gas. So like superconducting islands, and then you're hopping between the islands. That's at least that's.
Then these other components also get modified.
Well, experimentally, not so much. I don't know.
Experimentally, I think we are in a regime here where we are a bit far away from superconductivity. We observe the regime where superconductivity is important at higher resistance and further away in the transition on the more insulating side. Here we are in a regime, and tell me, Miguel, if I'm wrong, because you retweeted some of the data, which is mostly with fermionic. We are far away from the regime where we have a charging energy which is double due to the fact that we have a superconducting gap forming. And we have a paper on the other regime. If you want to, I can send it to you.
Maybe the problems with the sample anneal at 80 degrees is related to what you're saying.
Questions?
Maybe a very stupid question. So in the hot reaction model, you just equal the Joule heating with the dissipation. Does the heat capacitance matter? And how fast you increase the heat capacitance in the system?
Yeah, no. It depends on the speed at which you scan. Yeah. Okay.
But that's not in the model.
It's not in the model. No, exactly. This is not in the model. Probably when you jump from one branch to the other, this depends. Well, not probably. This depends on the speed at which you are scanning the voltage. So that there are dynamic effects here, but they are not included there.
When your sample is far from the insulating transition, it could also cool by electronic diffusion out of the sample. So this could explain maybe the fact that you have a different power law, maybe better conducting samples.
It's a bound system, so where does it?
Yeah.
It's a bound system, right? So where does it diffuse?
To the leads.
Other no,
it's a finite system, so you have leads. So
it's an insulator.
No, but it's an insulator. Yeah, it's a real insulator. So I think it can diffuse to nearby grains. That's what we are saying. That instead of being everything within the grain, other grains nearby also play a role. I got the leads play a role. No, I don't say no to anything. So I'm old enough to be careful.
I was wondering, so here you're in an insulator side of the transition, you have these grains, and you see that this electron-photon coupling actually revolves within the grain and then changes when it from transport across the grain side happens. Do you know of system where there is no morphological inhomogeneity and still these low holds?
Oh, here there are no morphological homogeneities.
You have
No.
grains.
No. Pseudo.
Okay.
I should say pseudo grains.
Okay.
Right? And Russians get very angry if I say grains. But
I
I don't see
would
any
have
here. I was encouraged enough to say
It's just
pseudo
sort of
grains all the
puddles
time.
that form, but not linked to any morphology actually.
So,
It's
yes.
like sort of puddles.
Yes,
like
no.
puddles that are insulating.
Electronic
It's-
emerging.
Okay.
Emerging granularity, electronic granularity, but there is no changing morphology.
Okay, so we can thanks Miguel again.